Right, welcome back. This is part 4b, chapter 4b of Laplace transform. In this part, we are going to use Laplace transform for ordinary differential equations. In this chapter 4b, section 1, reviewing ordinary differential equations first. So this is meant to be a review. We'll assume that you have some knowledge of calculus and differential equations. So let's revise. What's ordinary differential equations? Let's start with differential equations, which is an equations that contain derivative. So for example, here is a derivative of one or more known or unknown functions with respect to independent variable. So here the independent variable is x. So y is equals to, or dy dx equals to something of some function of f of x. So the other term we are using is called ordinary. So ordinary differential equation as opposed to partial differential equation. In ordinary, there is only one single independent variable. In our example here, the first one, the single independent variable is x. In the second one, partial, where we have more than one independent variable, then you can see that the independent variable is x and y, where u is our unknown function. So it's du, or a partial derivative of du and dx. Notice that the differentiation symbol has changed into this curvy d as opposed to this d, where this is reserved for ordinary and this is reserved for partial. Right, there are some terms that we need to classify differential equations. One of them is type, which is ordinary and partial. The other one is something called order and linearity. So let's try order and linearity now. What does order means? Order means the power of the highest derivative of the unknown function in the differential equations. Well, let's study this example. In here, the highest power is d1. So this is first order. Now this is using, there is only one independent variable, so this is ordinary. Okay, what about this second one? In here, the highest power is d2. So this is a second order. There is only one independent variable, so this is ordinary. And in the last one, the highest power is partial derivative d2, so this is second order, and this has two independent variables, so this is partial. Alright, with that, now we can come to the last terminology, which is something called linearity. We'll reserve linearity for the next page. But in brief, it is this term associated with the derivative that will determine whether the equation is linear or not linear. Alright, so linearity. Now, in general, we can, for ordinary, we are mainly focusing on ordinary here, so we have only one independent variable. So we have high order, so n can be 1, 2, 3, whatever we want. And we have ordinary nth order. Now, whether it's linear or not linear depends on this term here. So if in the case of this example, where the terms associated with the derivatives of the dependent variable, if these associate terms are only functions of x or are constants, and as long as it does not depend on y, for example, this term here is not sine y or some function of y squared root e to the power of y, then the above is an example of a linear differential equations. The second requirement is that the derivative, this part here, the dependent variable and its derivative must only be of first degree. So here is only to the power of 1. The equations does not have things like power of more than 1, or this derivative, even though it's power of 1, is to the power of k, where k is greater than 1. So to recognize whether it's linear or not linear, cast your differential equations in this form and study the functions associated or in front of this differentiation expression, and ensure that this function is at most a function of x or are constants, and make sure that they are not dependent on y. And this differentiation is of degree only 1. Let's now go to some example. So we are in this course, we are only interested in linear ordinary differential equations. So these are all examples of linear ordinary differential equations. So look at here. This is ordinary. We only have one independent variable. The functions in front of this differentiation expression is only of x or constants. The differentiation expressions only contain first order of y, and that's why this is linear. Now, how many order? This is third order, and this is ordinary. Alright, what about this guy? This guy is easy. This is second order due to this double prime here. The expression in front of this differentiation is constants, and here is 1, here's 1, so this is constant coefficient. Linear second order differential equation. How about this guy? This is y dy dx. So if everything divided by dx, then you will see that this is an expression for x multiplied by dy dx. We have y here and we have x only, so this is again in this particular case is first order ordinary linear differential equation. Alright, now some examples of nonlinear ordinary differential equations. Here y prime, so this is dy dx. The expression in front of this dy dx contain y, so immediately this is a nonlinear term. It's dependent on y, so this is nonlinear. Then where? Okay, so this is nonlinear first. Now there is only one independent variable, so this is ordinary, and this is first order. First order nonlinear ordinary differential equation. And here is one independent variable only, so this is second order. Only one independent variable, so this is ordinary. However, in the expression of power of y, once the first order, we have sine y. Therefore, this is non-linear. Okay. And lastly, here we again have ordinary, fourth order, and like our previous case, we have y, but it's not first order, it's second order. So y squared, so this makes it non-linear. So these are the examples of linear versus non-linear ordinary differential equations. Again, I repeat, we're only interested in linear ODE. In fact, later on you'll see in our examples, we're only interested in constant coefficients ODE. Okay, where the coefficients are simply constants. Right, thank you.